Our next section is 5.4 indefinite integrals. So what we just did was definite integrals. You found the area under a curve from 2 to 5, and you actually got an answer which was a number which stood for the area. Okay, the only difference here is now we're not going to actually go from a lower limit and an upper limit. What if I just want to find the integral of a function? Okay, that's indefinite. Indefinite means I do not have any limits. Okay, I don't have from a to b. Well, we already know. How do you find the definite integral? You just take the antiderivative. So an indefinite integral is just the antiderivative. That's all we're doing here. Okay, what I've done for you is put the table of antiderivatives just to remember. There they all are. We've been doing this the last section, so you should know this already. Okay, antiderivative of 1 over x is natural log of x. Antiderivative of anything to a power, you add 1 and divide by that new power, and then so on. You can look at these, okay? So these is your antiderivative list. So now, if you come down and you look at, say, number 1, it says find the integral of that function. That's really just saying find the antiderivative, okay? So this is the derivative of what? So what do we do? First term would be 10x to the 5th divided by 5, so 2x to the 5th. Okay, minus 2, and the antiderivative of secant squared is tangent of x. And now the only difference is you have to remember, just like before, when you do antiderivatives plus c. If it's indefinite, there could be any number there. We don't know, because when you find the derivative of a constant, it's 0. Okay? So then obviously I'd write this as 2x to the 5th minus 2 tangent of x plus c. So all these are really asking for, guys, all of these are just asking for the antiderivative of that function. Okay. Second one, you might say, how do I do that? Because I cannot do the quotient rule backwards. Well, if we're creative, we can rewrite this as cosine over sine times 1 over sine. Okay, all I did was I just split up the sine squared. And then you say, oh, cosine over sine is what? Cotangent. 1 over sine is cosecant. What's the antiderivative of cotangent times cosecant? Anyone? Would be negative cosecant. And then plus c. Okay. So with some of the trig ones, it might just have to get creative. Next one, pretty straightforward. What's the antiderivative of x cubed minus 6x? So it would be x to the 4th over 4 minus 6x squared over 2. Add 1, divide by 2. Simplify this. X to the 4th over 4 minus 3x squared plus c. Okay. Next one. I know I'm going fast, but this really isn't difficult. It's just understanding that an integral is an antiderivative. A definite integral is the actual area under the curve, which you still find the antiderivative. Okay. Next one, so go term by term. The first term would be 2x to the 4th divided by 4. So it would be what? X to the 4th over 2. Next term would be 6x squared over 2, or just minus 3x squared. Now you have to recognize what is, whenever you have x squared plus 1 denominator, this is tan inverse. So this would actually be plus 3 tan inverse of x. Okay, it's just remembering your 3 inverse functions, and then again, plus c. Okay, and then the last one is actually threw on a definite integral. So now I'm going from 1 to 9. Okay, cannot use quotient rule backwards. Can't just do numerator, denominator. Okay, so what do you do first when you're dividing by one term? You always simplify first. So change this by dividing every term by t squared. Okay, so this would turn into 2 plus t to the 1/2 minus t to the negative second dt. That's your first step. Now you can find the antiderivative of that. So antiderivative of 2 is 2t. The next one would be 2/3, what? T to the 3/2. Add 1 to 1/2, I get 3/2. Divide by 3/2, same thing as multiplying by 2/3. And then this would be what? Add 1 to negative 2, I get negative 1. Divide by negative 1, so this would become plus t to the negative 1. Now I don't need plus c because what? Now I'm going from 1 to 9, what we did before. Now you're actually finding the area under this curve. Okay, and if you plug it in, I'm just going to give you the answer. It's 32 and 4/9 if you actually get the value. So very different. A indefinite integral stands for a function. A definite integral is actually a number, which stands for the area under the curve. Okay? And then the second part here is talking about net change theorem. It's a big idea. It comes up a lot. We'll actually go through a packet in class on this. So here's the idea. If you take the integral of a rate of change, so if you take the integral of some rate of change, you're just getting the net change, which means the total amount from A to B. Here's some examples. Okay, if you have volume of water in a reservoir, its derivative is the rate of change at which the water is flowing into it. So if you take the integral of the rate of change of how much is flowing, what are you actually going to get? You're going to get the total amount of water between the time 1 and time 2. Okay, you can read all of these. You can do it with cost. We can do it with the next, here's what we do so much, velocity. Think about this one. The integral of velocity is just how far you went, because velocity is a rate of change function. This is how fast you're going. If I do the integral of velocity, what's the antiderivative of velocity is position. If I subtract the two positions, what do you get? I get how far I've gone, the total amount, the distance in that time. Okay? And then this, we have to be really careful. We'll do a lot of this. Is total distance traveled, just like before when we did this, we have to be careful, is absolute value. Because, if you don't use absolute value here of the velocity function, I'm just going to take where I ended and where I started, which is displacement. But I have to worry about if I change directions or not. That's all this is saying. Okay? And then the last one, acceleration. If I take the integral of acceleration, then you're going to get the net change in velocity from time 1 to time 2. Okay, and then here's one problem that I'll do out, which is total distance. And then we'll do more in class, like I said. Okay, so a particle moves along a line, so its velocity is given. Find the displacement of the particle and the total distance traveled. Okay, very different. Displacement is just where did I start and where did I end and what's the distance between them. So for displacement, I would just go from 1 to 4 of t squared minus t minus 6 dt. And that would give me my displacement. Okay, my total distance, I'd have to split this up, guys. I'd first have to figure out where I change direction, just like before. So set the velocity equal to 0. So I get what? T equals 3. The negative 2 doesn't matter. Okay, at 3 I change direction. So for total distance, you'd have to go see how far did you go from 1 to 3. Okay. And then add to that how far I went from 3 to 4. Because in one of these cases, the answer is going to be what? Negative. Because one of these, I'm going to be going backwards. So I'm either going forward and then backwards or backwards and forward. Okay, so we're really taking the absolute value of both of these. So if you do this out, you're going to take the absolute value of both of them and add them together. Okay, so displacement comes out to be negative 9/2, which just means what? I end negative 4.5 backwards or to the left from where I started. Total distance, you actually get 10.17 meters. That's actually how far you went. I don't care when I was going forward and backward, that's my total distance. Okay. I'm going to show you how to do this on the calculator too in class. But this is a big, big idea that we need to, it's just like what you did before. We've done this before with finding total distance. We just didn't use integrals before. You just used the position function, plug the numbers in, and subtracted them. Now we can actually say the integral of the velocity is the position function. Okay, I didn't show this work. I hope we're fine actually getting these numbers to actually get it to add to 10.17.